Another concept related to acids and bases that you want to know is what buffers do and how we can use titrations to figure out the relative or exact concentration of an unknown solution. So buffers are substances that help maintain a consistent level of pH. All right, so they are made by having a mixture that contains both a weak acid and its conjugate base. All right, this is important to know the two things that go into this. It's going to be a weak acid and its conjugate base. All right, and that means that we have both an acid and a base available to either remove H pluses or add them in based on what we add to our solution. All right, so thinking about this, we've got a weak acid and a conjugate base, which is going to be the part adding the H plus, the conjugate base or the weak acid. This is just remembering your basic definitions of acids and bases. All right. An example of a buffer is in us. All right. Human blood needs a very stable pH of about 7.4. All right. So is our blood acidic or basic? Hopefully you said basic. Carbonic acid and its conjugate base, all right, you can see it down here, is a buffer in our bodies that help us maintain this 7.4 pH. All right, so if you look at the molecules that are in your blood, you're going to have some of them in the carbonic acid state. You're going to have some of them in the hydrogen ion and bicarbonate conjugate base state. All right, so that kind of gave you the answer here, but the acid should be kind of obvious. It's going to be the carbonic acid. And then the bicarbonate, all right, this HCO3 minus is going to act as a base so that it can pick up H pluses, extra ones that show up in our bloodstream. Or the carbonic acid can split into the hydrogen ion and the bicarbonate base if there's a bunch of like OH minuses added to our blood. Titration is a procedure that will allow you to calculate or figure out the concentration of an unknown substance. All right, so what we can do is we can take an unknown substance and then add either a concentrated acid or a concentrated base, and then measure when this equivalence point is reached, right? Or the solution hits neutrality. All right, so you can actually, use litmus paper or something like that to measure when you reach neutral in your solution. When that happens, the concentration of the amount that you added of your known substance is going to be equal to the concentration of your unknown substance, or what it was at the beginning. So an example of applying this is you have a 215 milliliter sample of hydrochloric acid that you titrate with 0.1 molar NaOH. All right, so we know the concentration of the sodium hydroxide. The concentration of HCl, we don't know, and we want to figure that out. So we reach that equivalence point after adding 50 milliliters of NaOH. What is the concentration of the hydrochloric acid? All right, to do these, you just got to set up a proportionality. So I know my concentration of NaOH, and I know how much I added. All right, and this is going to be equivalent to my concentration of the HCl and its volume. All right, so I just need to set up this proportionality and calculate the concentration of the HCl. So that's going to require some cross multiplication. All right, so I'm going to have 0.1 times 215 is equal to X. I don't know what my concentration of the HCl was, but times 50 milliliters. All right, so I'm going to divide both sides by my 50 milliliters. And now I'm going to have x is equal to 0.1 times 215 divided by 50. Which, upon plugging that into a calculator, I get that my concentration of hydrochloric acid is equal to 0.43 molar. Another concept related to titration is using indicators. So instead of using an equivalence points, you can use an indicator that'll change colors when you reach a certain pH. All right, so for example, phenolphthalein will be pink until the pH falls below 8.3, and then the liquid will be clear. All right, so an example of using this is, let's say that both of these vials have phenolphthalein added to them. What can you tell me about the pHs of the liquids? All right, so remember, phenolphthalein changes from red to pink, from red or pink to clear when the pH falls below 8.3. All right, so what can you tell me about the pH of, say, vial A, since it is still pink? All right, pink means that our pH is greater than 8.3. All right, vial B, since it's clear, has a pH of less than 8.3. So which of those two vials is, say, more basic? Vial A, because its pH is greater than 8.3. All right, using an indicator, we can do some more complicated calculations to figure out unknowns, but you'll actually be doing it more in a relative sense. All right? So just kind of like the example on the last slide. If it's pink to start with, we know we're starting out basic. If it's clear to start with, then it's at least below 8.3. All right, so you can kind of, think about things in a more general sense. If I add 2 drops of acid to a vial that was pink, and then it goes clear, all right, then we started out basic, and not hugely basic. But what if I had a second vial that needs 12 drops to go clear? All right, so comparing the one that needed 2 drops and the one that needed 12 drops, which one was more basic to begin with? All right, if I need to add more acid to get it to drop below 8.3, then that means initially this vial with the 12 drops was more basic in the start because it requires more acid to bring its pH down. More basic to begin with.